In the history of space missions, there is one that, despite its humble beginnings, has become legendary. It was launched nearly half a century ago, at a time when the world was still unfamiliar with digital technologies and the depths of space as we know them today. The Voyagers, two identical probes sent by NASA, departed Earth with a singular goal: to uncover the mysteries of the outer planets of our solar system. But no one could have predicted that these spacecraft would embark on a much longer journey, providing humanity with knowledge about the boundaries of our stellar home. The Voyagers continued to deliver astonishing discoveries. Having left the limits of the solar heliosphere, they entered interstellar space, where they encountered phenomena that challenge conventional scientific understanding. The structures they have found, stretching across unprecedented distances, provide new information about our star's interaction with the galaxy and reveal previously unknown aspects of the nature of the interstellar medium. But what awaits them ahead? What mysterious phenomena lie at the distant frontiers that we are only beginning to comprehend? How will our perception of the universe change as the Voyagers continue to explore uncharted territories? And will they uncover secrets that have long remained hidden from our view? If the epic journey of the Voyagers inspires you as much as it does us, let's keep exploring together. Like this video to celebrate humanity's quest for knowledge, and subscribe to our channel to follow more incredible stories about the spacecraft, missions, and discoveries shaping our understanding of the cosmos. These legendary probes are still reaching beyond the boundaries of the known, and with your support, so can we. The longevity of the Voyager missions has become a true phenomenon in the history of space exploration. Voyager 1 and Voyager 2 are space probes launched by NASA on September 5, 1977, to explore the outer planets of the solar system. When Voyager 1 and Voyager 2 left Earth, NASA engineers could hardly have imagined that the spacecraft would be transmitting data decades later. The primary goal of the program was to study Jupiter and Saturn, planets that at the time remained largely unexamined. However, after the successful completion of the initial mission, scientists decided to extend the probe's flight, directing them towards more distant planets and beyond the boundaries of the solar system. This course adjustment marked the beginning of a truly unique research program. Having flown through the asteroid belts and the systems of Jupiter and Saturn, the Voyagers began transmitting data back to Earth, allowing scientists to gain deeper insights into the nature of these giants. An interesting mix-up occurred during the launch of the Voyager probes. Voyager 2 was launched on August 20th, 1977, while Voyager 1 followed on September 5th of the same year. The launch of the second probe was scheduled 16 days earlier than the first, because it followed a slower trajectory. This strategic difference enabled Voyager 1 to overtake Voyager 2 as early as 1979 and present the first data from its observations of Jupiter. To avoid confusion in public perception, NASA decided to invert the numerical order of the probe's designation. On March 5, 1979, the first encounter of the Voyagers with the Jupiter system took place. This flyby allowed the probe to photograph the planet's moons, such as Amalthea, Io, Ganymede, Callisto, and Europa, as well as to get close to the planet itself. During this journey, approximately 18,000 photographs of the Jupiter system were taken. One of the significant discoveries was the presence of faint rings around the planet, resembling those of Saturn and Uranus, which could not be detected from Earth. During its flyby of the moon Io, Voyager 1 captured the moment of a volcanic eruption, confirming the presence of volcanic activity on its surface. On November 12, 1980, Voyager 1 reached the Saturnian system. This encounter resulted in the acquisition of 16,000 photographs, including detailed images of Saturn's moons, Titan, Tethys, Mimas, Enceladus, Rhea, and Hyperion. The probe approached Saturn at a distance of 64,000 kilometers, allowing it to study the planet's temperature, 191 degrees Celsius in the upper atmosphere, and record powerful vortices at the equator, where wind speeds reached 1,800 kilometers per h. During its mission, Voyager 1 also discovered the largest moon in the solar system, Ganymede, with a diameter of 5,268 kilometers. On November 14, 1980, The primary mission of Voyager 1 to observe the planets of the solar system concluded, marking the start of a new phase, the extended mission of the spacecraft, during which it set out to explore the boundaries of the solar system with the aim of entering interstellar space. But what exactly allows these aging spacecraft to remain operational in conditions of radiation, extreme cold, and deep vacuum? How much longer will we be able to receive data from them as they approach new frontiers in interstellar space? And what discoveries are destined to occur next when the probe reaches Uranus and Neptune? After the successful exploration of Jupiter and Saturn, the Voyager 2 mission was extended, allowing it to journey even further, to Uranus and Neptune, two distant ice giants about which very little was known. These planets were beyond the reach of detailed observation from Earth, and it was through Voyager 2 that we made our first significant discoveries regarding their nature and unique features. On January 24, 1986, Voyager 2 made its closest approach to Uranus, coming within 81,500 kilometers of the planet. During this flyby, the spacecraft transmitted thousands of images of the planet, its moons and its rings back to Earth. These photographs led to important discoveries. 2 new rings were identified, and 9 previously known rings were studied. Additionally, 11 new moons of Uranus were discovered. Images of one of the moons, Miranda, surprised researchers. It was previously assumed that small moons like Miranda would quickly cool after their formation and would consist of monotonous cratered landscapes. However, it was found that its surface features valleys and mountain ranges, with rocky cliffs prominently visible. Miranda, also known as Uranus 5, was discovered in 1948 by Gerard Kuiper and named after Miranda from Shakespeare's play, The Tempest. This finding suggests that the moon's history is linked to tectonic and thermal processes. Moreover, Voyager 2 showed that both poles of Uranus have the same temperature, despite only one being illuminated by the sun. Researchers concluded that there is a mechanism for heat transfer from one part of the planet to another. The average temperature of Uranus is 59 K, or minus 214 degrees Celsius. On August 25, 1989, Voyager 2 flew within 48,000 kilometers of Neptune's surface. During this flyby, unique images of Neptune and its large moon Triton were obtained. Triton was discovered by English astronomer William Lassell on October 10, 1846, and is the 7th largest moon in the solar system and the only large moon in the solar system with a retrograde orbit. Active geysers were found on Triton, which was an unexpected discovery for such a cold, distant moon. 6 new moons were also discovered in late July 1989: Despina, Galatea, Larissa, Proteus, Naiad, and Thalassa. The exploration of Uranus and Neptune enriched astronomy with unique information that exceeded all expectations. These discoveries provided humanity with insights into the distant ice giants and their moons, revealing the richness and diversity of planetary systems beyond Saturn's orbit. But what awaited the Voyagers as they ventured further, beyond these planets, toward the very edge of the solar system? After passing through the outer planets and completing their exploration of Uranus and Neptune, the Voyager mission entered a new phase, setting its sights on the outer reaches of the solar system. At that time, knowledge about this area, known as interstellar space, was based solely on theoretical models. Where does interstellar space begin? Earth and all the other planets in the solar system exist within a giant bubble known as the heliosphere. This region is characterized by the space in which the plasma of the solar wind moves relative to the sun at supersonic speeds. However, as the distance from the sun increases, the speed of the solar wind gradually decreases due to collisions with matter from the interstellar medium. At some point, this motion becomes subsonic. The boundary where this deceleration occurs is known as the shockwave boundary. It is important to note that the shockwave boundary is not the final boundary of the entire heliosphere. Beyond it lies a region known as the heliosheath, or heliospheric mantle. In this layer, the solar wind experiences deceleration, compression, and turbulence. At the final stage, beyond the heliosheath, is the heliopause, the ultimate boundary where the solar wind completely halts. At this level, its pressure can no longer push back against the interstellar matter, resulting in a mixing of solar wind with interstellar matter in the heliopause region. Would the two Voyagers be able to leave the confines of our solar system and enter interstellar space? The answer to this question depended on several critically important factors. The first of these was the fuel situation. Each Voyager spacecraft regularly performed small maneuvers necessary to keep their antennas pointed at Earth. Fortunately, the spacecraft managed to conserve a sufficient amount of fuel, expected to last until the 2040s. However, another important issue arose on the way to interstellar space: communication. As they moved farther from Earth, the power of the Voyager signals steadily diminished, complicating communication with the spacecraft. Fortunately, thanks to several upgrades to NASA's Deep Space Network, this problem was resolved as well. Both Voyagers encountered various technical issues multiple times, but in most cases, specialists were able to either find a solution or switch the spacecraft to a backup system. Thus, the main factor determining the maximum possible operational lifespan of the spacecraft became the question of energy. The Voyagers derived their energy from radioisotope thermoelectric generators, RTGs, that use plutonium-238. The half-life of plutonium-238 is 87 years, and over the 45 years since launch, the generators have lost about 30% of their original output. Additionally, power loss occurred due to degradation of the thermocouples that convert the heat produced by the RTGs into electricity. Initially, mission engineers projected that the Voyagers would cease to receive sufficient energy to continue operating around the early 2010s, which would be insufficient for reaching interstellar space. In response, specialists developed a power-saving plan that involved turning off some scientific instruments and heaters. This approach proved effective, granting the Voyagers an additional decade of life, which ultimately allowed them to surpass another significant milestone. In late 2004, Voyager 1 crossed the shockwave boundary and entered the heliosheath, while its counterpart, Voyager 2, traveling at a slower speed and in a different direction, reached this same boundary only in 2007. By 2010, Voyager 1 had entered a region where the solar wind was experiencing stagnation, and its radial speed began to approach zero. Moreover, the number of high-energy solar origin particles began to decrease sharply, indicating that the spacecraft was nearing the heliopause. A historic moment arrived on August 25, 2012, when Voyager 1 was at a distance of 121.6 astronomical units, 18.2 billion kilometers, from the Sun. On that day, the spacecraft's instruments detected a sharp drop in the number of solar protons, and conversely, an increase in the level of galactic cosmic rays. Thus, Voyager 1 finally entered interstellar space. Voyager 2 crossed this boundary later, in November 2018, at a distance of 119 astronomical units, 17.8 billion kilometers, from the Sun. Existing models at the time suggested that crossing the heliopause should result in an instantaneous shift in the lines of the magnetic field. However, this did not occur, leading to a division among scientists. Some argued that Voyager 1 had indeed left the heliosphere, while others insisted that the spacecraft was still within its bounds. The dispute was resolved in 2013, when data indicated an increase in plasma density in the region where Voyager 1 was located. This data aligned with theoretical models for the interstellar medium. As for the magnetic field, subsequent measurements showed that its lines changed direction under the influence of the heliosphere not instantaneously, but gradually. Following this, the fact that Voyager 1 had entered interstellar space was accepted by all leading scientists. These discoveries about the structure and composition of interstellar space demonstrated that its influence on the solar system is much stronger than previously believed. But what else could the Voyagers discover as they continued their journey into the unknown regions of the galaxy, measuring new properties of the surrounding environment? How might the properties of this environment change further as the Voyagers delve deeper into unexplored areas of interstellar space? One of the most intriguing discoveries made by the Voyager spacecraft has been the strange and unpredictable structure of the heliopause, the boundary separating the solar wind from interstellar space. To date, They are the only spacecraft to have crossed the heliopause. These missions, along with the IBEX satellite, which studies the boundaries of the solar system and the neutral atoms formed as a result of the interaction of solar wind with the interstellar medium, have allowed scientists to establish that the heliopause can change its shape. A recent study led by Eric Zernstein from Princeton University, USA, revealed new unusual structures at the edge of the solar system. Researchers found that the heliopause is shifting, and significant asymmetry is manifesting in the structure of the heliosphere. This suggests that the boundary of the solar system is in constant motion. The results of this new study contradict previous scientific work and models of the heliosphere. Importantly, Voyager 2 is equipped with instruments that directly measure plasma parameters, such as density and velocity, which also allow for temperature estimation. In contrast, the corresponding instrument on Voyager 1 has not been operational since 1980, meaning all measurements of these parameters during its crossing of the heliopause were indirect, relying solely on magnetic field and particle flux measurements. The functional instruments on Voyager 2 have provided significantly more data. Now, scientists have a clear understanding of how the solar wind behaves as it approaches the heliopause, which will be useful for theorists developing relevant models. Data from Voyager 2 has allowed for the estimation of the plasma temperature outside the heliopause, which is between 30,000 and 50,000 Kelvin. This information is novel and interesting, as existing numerical models yield varying temperature values, and the measured data can now be used to test these models. The concentration of protons in the disturbed interstellar plasma just beyond the heliopause is measured at 0.039 particles per cubic centimeter by Voyager 2, while Voyager 1 recorded 0.055. This is generally consistent with theoretical estimates, indicating that the density has increased by approximately 20 times compared to typical values for the outer heliosphere, which are around 0.002 particles per cubic centimeter. Thanks to the Voyager spacecraft, the distance to the heliopause has been determined, 121.6 astronomical units for Voyager 1 and 119.7 for Voyager 2. The difference in distance can be attributed to the differing trajectories of the probes and can be used to estimate the asymmetry of the heliosphere's shape. Both spacecraft also measured the magnetic field outside the heliosphere. Voyager 1 recorded 0.49 nanotesla, while Voyager 2 recorded 0.68 nanotesla. This is a new and interesting observation that theorists will attempt to explain through numerical modeling. When Voyager 1 crossed the heliopause, it found that high-energy interstellar particles and the external magnetic field penetrated into the heliosphere. This indicates that the heliopause boundary is not a thin surface. There are structures of significant thickness present. In contrast, Voyager 2 crossed the heliopause in less than a day and detected a flow of solar origin particles beyond it, as determined by their energy, which was lower than expected. Thus, near Voyager 1, interstellar particles were found inside the heliopause, while Voyager 2 recorded solar particles outside. All of this data consists of direct measurements, and their interpretation is conducted using model calculations. However, current studies focus exclusively on the measurements themselves. Researchers have characterized these discrepancies as intriguing and potentially contentious, as they suggest that the heliopause has in fact shifted by dozens of astronomical units over this period. Moving forward, scientists plan to continue studying the heliopause and hope to obtain additional data from the Interstellar Mapping and Acceleration Probe spacecraft, which is set to launch in 2025 to study the edge of the solar system. Completing the Voyager mission and summarizing its findings, it can be said that these spacecraft have unveiled previously unknown aspects of the interaction between the solar system and galactic space. Although an enormous amount of information has been accumulated over the more than 40 years of the probe's operation, many questions about the nature and structure of the solar system's boundary remain unanswered. These intelligent machines, like keepers of secrets, have paved the way into the unknown. Each of their measurements, every recorded signal, is a piece of a mosaic that helps scientists better understand how our stellar system interacts with its environment. However, with each new discovery comes even more questions. This becomes particularly relevant as we look toward the future of Voyager 1. In 28,000 to 80,000 years, when it leaves the boundaries of our solar system, its fate will exemplify cosmic wandering. It will move through the vast expanses of the Milky Way, orbiting its center alongside other stars. Yet its speed, necessary to escape the galaxy's gravitational pull, is unlikely to be achieved. The probe will remain in orbit, becoming part of the galactic ecosystem. Despite its long journey, Voyager the first may encounter asteroids, which could lead to its destruction long before high-energy photons ultimately ravage it. Still, if it manages to avoid such collisions, this probe will continue its wandering through the galaxy even when Earth and the other planets have long since disappeared and the Sun has become a white dwarf. These spacecraft, having become symbols of scientific progress, will carry on their journey, relaying the story of their endless odyssey and perhaps leaving traces of our existence in space. Subscribe to the channel and stay tuned for news so you won't miss fresh discoveries and the most exciting moments from the world of space.